Method, types of antennas, single port measurements, and two port measurements. So first thing is where are antennas used? And antennas are used anywhere there's a transmission or reception of a radio. And we'll find these in satellite communications, terrestrial communications, radar, and sonar. Antennas are reciprocal devices, so they're operating in both directions equally efficiently. So radio waves, very quickly as a review, radio wave is a magnetic field at a right angle to an electrical field. Both fields travel oscillating together and are perpendicular to each other. These electromagnetic fields travel at the speed of light in free space, and our understanding of these are based on Maxwell's equations. So some terms we need to know about antennas if we're going to perform measurements. Polarization is the orientation of an antenna to the earth. A vertical polarization is when the antenna's electrical field is vertical to the earth's surface. Horizontal polarization is when an antenna's electrical field is horizontal to the earth's surface. And then we have near fields and far fields. Near field antennas are very close, and they're generally a couple of wavelengths of the operating frequency to a near field antenna. And an example of that is RFID, when you use your credit card to swipe over a scanner to pay. And then far fields are further away from an antenna, usually at least 10 wavelengths of the operating frequency from the antenna. And those are most common that we see today. The other subject to talk about when thinking of antennas are antenna gain. And antenna has gain, and you can find that gain in the technical data sheet from the manufacturer. And depending on the type of antenna design, there can be more than 50 dBi of gain, and those are generally parabolic, large satellite antennas that have that much gain to them. Others, more general antennas, they'll have about 20 dBi of gain. And we achieve that gain by utilizing elements on the antenna, and the elements direct the energy in a specific direction. When we talk about I in dBi, that stands for isotropic, and isotropic antenna is a perfect ideal antenna. And if you would imagine that you had an orb that emitted energy in every direction equally, that would represent a theoretical isotropic antenna. But because no antenna actually really operates in that fashion, we have directional antennas. So a good way to think about that is if you can imagine a light bulb that shined in every direction equally, it would propagate all of that energy that would have no gain whatsoever. But if you took a mirror and angled the mirror at 45-degree angles, the light would shine more brightly in the direction of that 45-degree. That's the same concept for antennas. That's how antennas have gain. There are a lot of different types of antennas, isotropic, dipole, monopole, array, phased array antennas. Those are utilized primarily for beamforming. And there's quite a few interesting advances in chips where the chipset can adjust the phase of a signal and create a beam, and that's in a lot of 5G technology and things like that that are coming forward. Conical antennas are used in satellite applications and point-to-point. They're also beamforming, and then we have aperture, which are waveguide horn antennas. You'll see those in a lot of different applications. So here's an example of a 2-port antenna application. In this case, this is a radar cross-section measurement that's being performed on one of our handheld VNA masters. And then here are some other examples of where antennas are. We have cellular communications, military aerospace, medical telemetry, land mobile radio, first responder radios, of course, AM, FM broadcast, WLAN, those types of things. And as you can see from the ship, there are many, many antennas, and the base station that you can see a gentleman climbing on, many, many antennas on that mast. And when we talk about antennas, we have to measure across the entire spectrum, and we can do that with different models of Anritsu vector network analyzers, whether they be benchtop, they can go up to terahertz range. And we also have handhelds, very common in cellular base station maintenance, where the cables and antennas are measured as well. So first thing we have to do in order to measure an antenna's performance is determine the specifications from the technical data sheet, and that is going to tell us what the start frequency is, what the stop frequency is that the antenna is designed to operate in. And then we're going to choose the number of data points and IF bandwidth, and we'll set up the traces for our desired measurements. Of course, when we set up the VNA, we're going to have to perform a calibration to establish our ratio. And in this case, we'll use an SOLT method. The antenna that I'm using today is a 3.5 millimeter connector. So these are the common types of calibration. There's many different types. Obviously, if you have aperture where it's waveguide, that type, you might utilize a plate, a reflection plate, things like that. But there are many different ways to perform a calibration. And just as a refresher, so that we understand what our S parameters mean, S21 is our forward transmission, S12 is reverse transmission, S11 is our forward reflection, and S22 is our reverse reflection. And here's some definitions if you actually want to understand how the VNA is performing the math for the ratio. You can look at all of these as well. And we have our Smith chart, which is very important in order to measure our S11. We're always going to be looking for a match in the center of the Smith chart at the operating range of the antenna. Excuse me. So here I'm going to show some examples of how to set up the VNA. This is on a Shockline series vector network analyzer from Anritsu. And we have our start frequency of 3 megahertz, our stop at 3 gig. Number of data points chosen is 1,000. And we're going to set up our traces. You can set up as many traces, up to 16 traces with different parameters on there. In this case today, we're set up 4. And under display, we can change that trace format and change the measurement to what we like. And under calibration, that's where we're going to set up our cal. We're going to do a manual calibration. Sorry. And we're going to do a 1-port. And this is where we can modify the cal setup. And then, of course, when we select port 1 devices, we're going to calibrate, connect our open. And once the open is measured, you'll see a checkbox once that device is measured. And then we connect a short and select short. When it's finished, again, you'll get the green checkbox right there. And then we have to connect our load. Once our load is finished, again, we get the green checkbox. After that, we click done and the calibration is applied and we connect our device and can perform a measurement. And that could be in frequency domain, time domain. You can look at SWIR or Smith chart or whichever you really need to measure. We also have time gating in time domain. And you can measure the length of cables, obviously, that are connected to the antenna that are on the tower, or measure different devices. In this case, we're just looking at an open. Then, of course, there are times when you may want to have a 3D representation of your antenna, and that is achieved with a vector network analyzer as well. And what happens is you have the antenna in a fixed position, and most of the time you have a robotic arm within a chamber, and that robotic arm will travel to different coordinates in a circle entirely around the antenna. And what it'll do is it'll save an S2P file for each position. And then once the robotic arm is finished covering all the coordinates, those S2P files are used to calculate a 3D representation of the energy surrounding a antenna. And in this case, it's a half-wave dipole antenna, and that's going to give you a donut-shaped representation in 3D. And now we will pause for a second and we'll take any questions, and I'm going to switch over to the VNA. Great.
Okay, go ahead. I'll let you type your question in there. Let's see. Yes, he has a question, so go ahead. I'll give him a second here. Oh, okay, ready? The calibration is always in the SOL order?
Yes, you should always follow the SOL order on any VNA. Most of the time it won't have any impact, but just organizationally, it's always best to follow the instructions on the VNA. In our case, you're always going to find that the VNA, regardless of the VNA type product that it is, it's always going to be open, short, load, and then the through. And of course, if you're doing a 2-port, you always want to characterize the through being reciprocal, or you want to know the exact electrical length in picoseconds or millimeters. So.
Okay, I do have another question for you. Actually, they're coming in now. So, is the BW of the antenna the same as the band between the start and the stop frequencies?
Yes, that's what you would set your bandwidth, the bandwidth of the antenna. Every antenna is designed to operate in specific bands, specific start-stop frequencies. If you think of them, they're the way that they're designed, they're sort of help you in, they act as a filter, if you would. So the bandwidth is always the start frequency and then the stop frequency of the antenna.
Okay, the next question is, for an antenna mount on a tower, how can you eliminate the effects of receiving signals during antenna measurement with the VNA?
You can't. You would have to put the antenna in an isolation chamber. And so you really don't have that opportunity.
Okay. Can you just leave the port open, or do you need to use a calibrated open and short?
You always have to use an open. You can't leave it open air. And the reason why you can't do that is a precision open from a calibration kit that is designed to operate in a 50 ohm network. And if you leave the port just open to air, it actually sees approximately 376 ohms, I believe, open to air. So it's not a correct match. And if you remember the Smith chart that we looked at, we're always interested in having a precision match. That is what establishes the ratio that allows the VNA to make accurate measurements.
How far the antenna be placed? Is the measurement needs to be done in a shield room? How about open space measurements?
So I guess that person is probably doing material measurements, which are very common, two-port antenna measurement for a VNA, where you have two antennas and you calibrate generally with a reflection plate in the center. And you have both ports then, once the VNA is calibrated, can measure the material and determine the propagation velocity and dielectric constant of the material. The length that the two antennas should be separated at, in general, you want to have, if it's a far field antenna, you want to have about 10 wavelengths away from both antennas. So it's dependent on the operating frequency that you're utilizing. Obviously, very low frequencies, the waveform can be as big as a football field, and whereas millimeter wave lengths are measured in centimeters. So it depends on the frequency of the material, the frequency that you're measuring the material with. But in general, you probably want to be about 10 wavelengths away.
Okay. Can I use this system when testing the signal efficiency between a transmitter and a receiver?
Well, that's what the VNA is doing for you. You established a ratio on a two-port VNA. When you measure those antennas, the magnitude level, that's telling you the efficieny. And if your two antennas are matched to the center of the Smith chart in reflection of S11 and S22, and the direction is correct. Remember, we talked about polarization, whether it be vertical or horizontal. You want both those antennas to be the same for maximum transfer of energy.
In case you do not know the BW, how can you determine it? Could it be measured or calculated?
Yes, it can. The most common way, if you're trying to determine a device's frequency of operation and you don't have a technical data sheet or a model number, you would, your first clue is going to be how the device is connectorized. So if you have a 3.5 millimeter connector, it's going to go it's not going to start to mode until after like 33 gigahertz. If you have 2.92 connector, you know that the maximum frequency is going to be 40 gig. If you had 1.85 millimeter, your maximum would be 70 gig. A 1 millimeter would be 110 gigahertz, and so on. So the first thing I would do is look at how it's connectorized, because that's going to tell you what the top frequency is. And then you would calibrate the VNA to sweep. Imagine you had a device you didn't know what the frequency of operation was, but it has 2.92 millimeter connectors on it. So you'd utilize a 40 gig vector star VNA. You would calibrate from 70 kilohertz to 40 gig, perform that calibration, and then connect the device to it. And whether you're looking at S11 or S21, if you have two connectors, depending on your measurement. If you're looking at S11, where the frequency lands closest to the center of the Smith chart, that's the operating frequency of that device. And that's how you determine what the bandwidth is. And you could back it off by, if you looked at it in log mag, you could back it off by 3 dB, and that would tell you what your start and your stop is.
Can you explain dithering or RF high immunity in the VNA?
Well, dithering has to do with averaging, which generally you're not going to utilize with the VNA. And what was the other part?
RF high immunity.
So RF immunity. So each VNA and a lot of cables, they have RF immunity from outside sources, but that's in regard to the instrument itself, the immunity the instrument itself has. Of course, if you're measuring an antenna and you're in an outdoor range and there's a lot of energy in the frequency range that you're measuring, you're going to have energy getting into your measurement, and you're going to have to make adjustments for that.
Okay, how does the length of the cable affect the measurement results?
Well, it depends on, oftentimes when you're measuring a cable and antenna and you can't disconnect them, the cable obviously is part of your measurement, and the specification that you're going to have for that combination is going to be cumulative in terms of SWIR. So, the cable is going to be part of your measurement in addition to the antenna, and that's very common.
Okay, does this webinar also apply for coaxial cables?
Yes, it does. It doesn't really matter what type of cable. Could be waveguide, it could be coaxial, helix, all kinds of different things. The principles are all the same.
Okay, does having an antenna cable length too long matter when installing antennas?
Well, you always want to be cognizant of the dynamic range of the VNA. Obviously, if your cable length has a large loss per foot, and you can, you could quickly eat up the dynamic range of the VNA. So when you're selecting a VNA, that's one of the things to consider, is how much dynamic range do I need for my measurement? And oftentimes you'll find that many VNAs have 100 dB and sometimes greater in different frequency ranges, and that overcomes a very long cable length that has a great deal of loss per foot. But in general, you can get pretty good distances, in thousands of feet.
Okay, my last question here. The phase shift, would it be different based on distance? And then the other part of this question is, how does the VNA take care of the phase delay and group delay?
Well, group delay is actually a measurement that you want to perform because you want to know how long it takes in terms of picoseconds for the signal to travel through that cable or material. That's a very, very common measurement. And can you repeat that question about the phase part?
Right, phase shift, would it be different based on distance?
No, your phase shift is not going to be different over time. Obviously, as the signal is propagating through the material, the phase is constantly changing. But if you have to perform a phase match of a cable, that can be done as well. You just simply turn off wrapping on the VNA, and then if you turn your marker on and scroll the marker down, you'll have basically a line descending in generally a 45-degree angle, and as you move the marker down that unwrapped phase, it'll tell you the exact phase at different frequencies.
Okay, great. Thank you so much, Tom. That was it.
Okay, great. Thank you. I appreciate it.
Thank you. So on behalf of Anritsu and our presenter, I want to thank you all for joining us today. This concludes our presentation. Have a great day. Goodbye.